Okay, so exponential growth and decay factors. Let's look at an exponential growth curve. And an example of this would be the population of the world. It stays pretty level for a long time in human history, and then we got the agricultural revolution, and it goes up like that. It's exponential. There might be some little blips in there from some different times the population has gone down, but in general, it's going to be exponential, an exponential growth curve. Okay, exponential decay might be like the price of a car. When you drive it off the lot, it's expensive, and then its value goes down really quickly over time, and then it levels out when it's just worth scrap metal or whatever, right? Okay, so just to get an idea of what a growth curve and a decay curve would look like. All right. So an exponential function is going to have a variable in the exponent. So this question right here, is y equals x squared an exponential function? Some people are going to say yes, and I understand why, because it has an exponent, but it doesn't have a variable in the exponent, right? This is actually a quadratic equation or quadratic function. It's not exponential. So my answer is no. Okay, y equals x squared is not exponential. This is going to be exponential because you see I've got x in the exponent. So that's what makes this one exponential. Okay, so y equals 2 to the x is our very basic exponential growth, our most basic exponential growth function. So we're going to graph this because it's going to be a parent graph. Okay. And a good way to start always when you've never graphed a particular type of function is to make an XY table. We'll get some points, plot them, and then we can get a sense for what the function will look like. Okay, so I'm going to plug in these different values for x into this function. Okay, and I'm not going to write these all out. I'll just start doing these in my head after a while, but 2 to the 0th equals 1. So when I plug in 0 for x, I get out 1, right? And when I plug 2 to the 1st is 2, and so forth. Okay, so 2 to the 2nd is going to be 4. 2 to the 3rd is 8. 2 to the 4th is going to be 16. Okay, now let's plug in some negative numbers. So if I have 2 to the negative 1st, remember that's y over 2 to the 1st, so that's 1/2. So this one will be 1/2. And then 2 to the negative 2nd, that would be 1 over 2 to the 2nd, so 1/4. Okay? So 2 to the negative 3rd is going to be 1/8, and 2 to the negative 4th is going to be 1/16. Okay? So let's try plotting those. So I'll start from the top here. 0, 1. There we go. And then I've got 1, 2, and 2, 4. 3, 8, 4, 16 is in the very top right corner. So we can see this is going up pretty quickly. It's going up exponentially, in fact. It's going to keep getting steeper and steeper. Okay? And as we go to the left on this graph, it's going to level out. So, yeah, negative 1, 1/2. It's right here. Negative 2, 1/4. That's even closer to the x-axis. And it gets pretty hard to graph this, but, you know, negative 3, 1/8 is going to be really close to the x-axis, and then 1/16 even closer. Kind of just looks like it's on the x-axis, but I'm trying to represent it's barely above. And you get a sense for what's happening here. We've got a curve. This is an exponential growth curve. Okay, so it'll look something like that. Okay. Now it's no matter you see with these negative numbers. If I put in negative 5 or negative 6 or negative 7, it's still not going to reach 0. Even if I put in negative a million, it's going to be 1 over 2 to the millionth. So it's going to be 1 over a really large number, but it's not going to be 0. So what's happening down near the x-axis is these, as we go to the left, these numbers are going to approach 0. It'll get closer and closer as we go to the left on the x-axis, but it will never, ever get there. So this is an asymptote. This is called, well, this one is a horizontal asymptote. And that just means It's the curve is never going to, it's going to approach this but never cross or never reach. Can't touch us. I'm just writing curve approaches but never reaches. Okay. All right. Okay, so that is our parent graph for growth curves. All right, so let's talk about finding the y-intercept in different exponential functions, because that's going to be useful. So the y-intercept is going to happen, it's where my curve is going to cross the y-axis. It's going to happen when the x value is 0, right? Because I'm not going left or right. I'm just staying on 0 for the x's, but then I have to go to wherever it crosses, okay? So plugging in 0 to find the y-intercept. So 3 to the 0th equals 1. So my y-intercept on part A is 1, okay? Hey, my y-intercept on all of these is going to be 1 because when I plug in 0 for x, I've got something raised to the 0th power. It doesn't really matter what that something is. Okay, so for your basic exponential growth curves, the y-intercept's always going to be 1. Now, things will happen when we can move that around by making these equations more complicated. But if you just have y equals something raised to the x, it's always going to be 1 for your y-intercept. Okay? Okay, on to the next page here. So there's a way that you can tell if something's exponential growth or decay based on the base, okay? And I'll get to what exactly the base is in just a second. It's just the part that's raised to the exponent, okay? So actually looking at this exponential function down here, the whole contents of the parentheses here is the base. This is the base because that's what's raised to the t here, okay? So technically it's actually the absolute value. If that's greater than 1 of the base, then it's going to be growth, and if the absolute value is less than 1, but you can, most of the time you can just think of it's greater than 1 or less than 1, okay? All right, if it's exactly 1, it's not going to grow or decay. It's going to stay at the same level. There'll be a horizontal line if the base is 1, okay? All right, so I'm going to first talk about this kind of in terms of money because it's the easiest way to describe exponential growth. Okay, so let's say we have a bank account and you put some money in the bank account. That where the A is in this equation, that's going to be where we would put the money. So I'll call this your initial amount. Now, this doesn't have to be money in a bank account, right? But it's an initial amount of something that's going to go up exponentially, okay? And then y is going to be the final amount. So in the bank account analogy, that's what we would have in the account when we take it out after some amount of time, okay? Speaking of time, I've got a t here. Sometimes you'll see this as an x, but most of the time we're going to be using time for our exponential function. So this is going to be our time. Generally, it's in years. That can be different, but usually we're going to go in years, okay? The R is going to be the rate, okay? So in a bank account, let's say you get 6% interest. Your rate is 6%, but you want to write that as a decimal. Okay, so just to use that same example, 6% would be 0.06, right? So we would write it like this for the equation this way, okay? All right, so let's try this out. So the only difference really between growth and decay is if it's increasing or decreasing over time. So that would be if you're adding the rate or subtracting it, really. You can think of it like that, okay? All right, so here's our first example. Funkytown has a population of 20,000 people. The population increases 4% per year. So let's write an exponential function modeling this, okay? So our initial amount is going to be the 20,000. That's the population at the beginning of this problem, okay? And then we've got 1 plus something in here. And the something is the rate, so that's going to be 0.04. Don't write it as 4. That's going to be wrong, okay? And then we're just going to leave the t as time. So that way we can plug in any amount of years and figure out how many people would live in Funkytown. And yeah, you can simplify this a bit, but you can't really do too much with it. That's as far as we can go, okay? Some people are going to multiply the 20,000 and the 1.04, but you don't want to do that, okay? So this is incorrect. I need to figure out what 20,000 times 1.04 is. Just 1 second. So that comes out to 20,800. So some people are going to simplify it to that, but don't do that because the 20,000 is really raised to the first power and the 1.04 is raised to the t, and so you'd have to do the exponents before you multiply, and I can't do the exponent because I don't know what t is. T is unknown, okay? So this is as good as we can do. All right, excuse the bell there. So what will the population be after 12 years? Now that I have this function, all I have to do is plug in 12 for the time, for the amount of years, okay? And then I'm going to simplify this. I'm going to do this with my calculator because I don't know what 1.04 to the 12th is off the top of my head. But my calculator does. So 1.04 raised to the 12th power. Make sure you do the exponent before the multiplication, right? So, okay, there's after the exponent, and then I'm going to multiply that by 20,000. And I've got that. Okay, now this is population. So yeah, I could write this as a decimal, but we're not going to have 0.6 people, right? So I'm going to round this to the nearest integer, to the nearest person. Okay, so I'll call this 32,021 people. I will put about because it's not exact, right? But that's to the nearest person. 22,021 people, sorry, it's rounding up to the nearest person. Okay, when will the population reach 70,000? Well, I'm going to use this same function that I wrote, the same equation. Okay, and 70,000 is going to be the final amount, so I'm going to plug 70,000 in for y. Okay, now I'm trying to solve this for t, so I'm going to think, what can I do? Well, I can divide the whole equation by 20,000. Okay, so then those 20,000s are gone, and I just have 1.04 to the t over here. Now, all of my zeros are going to cancel out here, right, on both sides. So 7 over 2, 7 halves is 3.5. So I've got it down to this, okay? Taking the square root of both sides won't do me any good because then I'll just have the square root of 3.5 and the square root of 1.04 to the t. And I can't really take a root with an index of t because I don't know what t is. Okay, so there is a way to solve this, and that's really what this chapter is about. But we need logarithms, and we don't have them yet. So for now, we're going to do a guess and check kind of thing. Okay, now you could just take 1.04 and say, okay, well, I'll raise that to the second and see what I get. And I got that, but I'm trying to get it to say 3.5. Okay, so you can just play around with it, but it might take a while to narrow in and just throwing out different numbers. Okay, that's way too big. I know it's going to be between 2 and 99. But let's think of a nicer way to do this. If I just plug, I can graph this on my calculator, and then I can move my cursor around and see the XY pairs, or I can also make a table, okay? So that's what I'm going to do. I'm going to hit the Y equals button, and I'm going to clear whatever was there already. I'm putting in 1.04 to the, and then my variable button is right here. Right? That's where I get the x. okay? And then I'm going to hit graph, and I'll see what this looks like. This should be exponential growth curve, and it's not growing much yet, but that's because of my zoom, okay? So what I can do now is if you hit the trace button, then you'll get a cursor that's stuck to the curve. And I can move this, so I can move this until I get a y of 3.5. Now this is taking a while. I'm still on 1.2, 1.3. It won't take me that long, but to make things a little quicker, what I could do is zoom out so that my cursor gets there quicker. Okay? So I'm going to zoom out. It's just going to zoom out where my cursor is over here. And it should draw the curve again. I'm just going to give it a second. Okay, then I can see the curve over there, and I'm going to do trace again. And now when I move my cursor, it's making a lot bigger jumps. And at the bottom of the screen, I'm looking for a place where y is about 3.5. It's not going to be exact, so it's somewhere in there, right? So it looks like it's about 31.7, 32.5. Between those, it's about 32. So my guess is going to be about 32 years. After about 32 years, oh, sorry, this was the 3.5. After about 32 years, I'm going to get 3.5 there, okay? So my final answer here, about 32 years, okay? Now, it's just a guess and check kind of thing, and we'll get a more accurate answer and a quicker way to do it later in the chapter. Another thing you can do is look at, if you do table right above graph, if I hit second graph, then it gives me an XY table, and I can kind of just scroll through these. All of these points are on the graph, so I can go look down. And remember I was saying about 32 for X gives me about 3.5. Yeah, and that looks pretty good, right? 32 looks pretty decent. It's not exact, but it's pretty close. Okay. Okay, next page. So here we've got a car that cost $15,000. And I just remember there's a typo here, so let me fix that. Okay, so a car cost $15,000, and it depreciates at 7% per year. So we're going to write a function. It's going to look a lot like well, it is the growth formula, except it's actually decay. So my initial amount is 15,000. Okay, and then instead of doing 1 plus my rate is going to be 0.07, right? 7%. But instead of adding it, if I'm adding it, then it's going up 7% a year. It says it depreciates, so this is actually decay. So the only difference is you're going to subtract out that rate, okay? And then this is going to be my time up here, okay? So I can clean this up a little bit just by doing the subtraction. So that's going to be 0.93. So that means, every year it's going to be 93% of the previous value that it was, okay? All right. So what will it be worth after 9 years? Well, I'm just going to plug a 9 in for t into the formula I just wrote. Okay, and then in your calculator, make sure you do the exponent before the multiplication. Want to use PEMDAS here, right? So I'm doing 0.93 raised to the 9th, and then multiplying that by 15,000. Okay, and then since this is money, I'm going to round to the nearest cent. So I'm going to call this $7,806.17. Here. Okay, so that's how much it's worth after 9 years. When will the price reach $2,000? Not the population, the price. Okay, so I'm using this same formula from above, except I'm not going to put the 9 in because I'm using this formula really, right? I don't know what the time is yet. Okay, and instead of putting in t, it's fine to put a t here. This is what I'm looking for, but I'm actually going to write that in as an x just because I'm going to end up using my calculator to graph this. Okay, so I want to know when the final price is going to be the y, when that is going to be $2,000. Okay, so y is going to equal 2,000 when x equals something. That's what I'm looking for. Okay, and if we had logarithms on our side, which we will soon, but we don't yet. If we had logs, we could get an exact answer pretty quickly, but we're going to have to do a little guess and check. You can just start plugging in numbers for x, but that might take us a while to narrow in on this. So what I'm going to do instead, let me put my calculator over here so it shows up better. All right, what I'm going to do instead is graph this function, and I'm going to look for xy pairs where the y is close to 2,000. Okay, so let's see. I've got 15,000 times 0.93 raised to the x, and x is this button right here, right? Okay, and you could put the exponent on the outside of the parentheses. That should be fine. Okay, once you got it in there, hit the graph button, and I have a weird graph going on my calculator, weird zoom going on my graph right now. Yours might look a little different. Okay, but you could play around with the zoom. As long as you can see the curve, then it should work out pretty well. Okay, if you can't see the curve, hit the zoom button, and you could go down to zoom fit. On mine, that's the 10th option down there, and if you hit that, it should show you the curve. Okay, and that's what I want. It's redrawing it now. That's what I want, because what I'm going to do is hit the trace button. And then I'm going to get a cursor. It's kind of way at the bottom of the screen here, but I can move this around, and it should be stuck to the curve. And at the bottom, as I move this around, it's going to generate xy pairs. So I'm looking for when is the y 2,000, right? So right now it's at 29,000 something. Okay, so I got to go to the right. Got to make that go down a little bit. Well, quite a lot, but it's going down quickly, right? And if this were moving too slowly, you could zoom out or zoom in, and then the jumps will go slower or quicker. But I'm getting to 2,000 pretty quickly here. Okay, so you can see this is maybe a little hard to see, but it's 2046, I think, and then the cursor is right in the way of the y number. But it's between these two spots, and then when I look at the x's, that's between 27 and 27.4 and 28.3. So, anywhere in that range is a decent estimation. So you can, I'm just going to say, I don't know, 27.8 or something like that, or 28 even would be fine. I'll just go to a nice round 28. After about 28 years, the price will be $2,000, somewhere close to that, okay? So, yeah, if you zoomed in a little bit, then the numbers would move slower and you could get a more accurate answer. You can also create an XY table by hitting second graph. So if you do that, then you get an XY table, and you can just kind of jump up and down on it. So I can see, okay, it's between 27 and 28 years when it's at 2,000, right? And you can estimate where exactly between it is, okay? All right, next up, we've got $200 that's invested at 4% interest for 10 years. I'm going to use exponential growth formula. Okay, so that's this, right? Okay, so y is my final amount. My initial amount is $200, and it's going up 4% per year, so I'm going to add 4% to the 1, okay, and then I'm going to leave it in there for 10 years. Okay, and then it's calculator time. I'm going to use my calculator to raise 1.04 to the 10th first. And then I'll multiply that by 200. Okay, and then rounding the nearest cent, that's going to give me $296.05. Okay, now when it doesn't say anything about compounding, which I haven't explained yet, but that means we're actually compounding once per year. And what compounding is, that's when you're taking the percentage, okay? So imagine this bank account. We start off with the $200, but then at some point you have to take 4% of 200 and add it back into the bank. And that's what compounding is. It's when you put the 4% in. So if it's not mentioned, it's assuming that at the 1-year anniversary of when you put in the $200, that's when you add in 4% of 200 to the bank, Okay, and at the end of the second year, you'd add in 4% of whatever the new total was, and so forth. Okay, so compounding is the interval at which interest is reinvested. Okay, now this doesn't have to be money and investing, right? But it's the interval at which you take the percentage of something that's growing or decreasing. Okay, all right. So we can actually use this formula when we're compounding annually, and I'll show you an example of that. Now the new feature here are the ends. Okay, everything else is the same as before. N is the number of compounds per year. Okay, so we've got $100,000 at 6% interest for 9 years, but this time we're going to be compounding at a different interval. So let's find the balance if it's compounded annually, just like this was compounded annually. Okay, so using this formula here, got $100,000 as the initial investment. Okay, the rate is going to be 6%, so 0.06. Okay, number of compounds per year. When it's compounded annually, that means you're compounding once per year. Okay, so I've got a 1 up there for that other n, and the time is 9 years. So the 1's don't really do anything because 0.06 divided by 1 is just 0.06, and 1 times 9 is just 9, right? So that's why you can use just this formula. You don't really need the n's because they're just 1's and they don't do anything, okay? But if I simplify this a little bit, let's see, that's going to be, I can simplify it without a calculator a bit. Okay, and then I need a calculator from there. I'm going to put 1.06 to the 9th. And then multiply that by 100,000. So I've got $168,947 and 90 cents, rounding to the nearest cent, right? Okay. All right, so let's see what happens when we compound semi-annually. So this means we're compounding twice per year, right? 2 semesters in a year, so that means, compounding twice per year. So it's really the same exact formula up here. It's just the 2 ends, these are going to be 2's, right? The ends are going to be 2's. So since you're adding the 6% in more often, we should get more money, right? So let's see if that happens. Okay, so sorting this out in my calculator, I'm going to start right there. So 0.06 divided by 2 is 0.03, and I'm going to add that to 1. Okay, so the contents of the parentheses will be 1.03. That's my base. 2 times 9 is 18, and then it's calculator time. Okay, 1.03 to the 18th times 100,000, and let's see, 170,000 rather, $243.31. Okay, so as predicted, we got more money when we put in the interest into the pot more often, right? Okay, get about, I don't know, $1,000 and some change here, $1,500 or something, okay? All right, monthly means, hey, 12 months in a year, we're going to be compounding 12 times per year. And daily, if it's not leap year, we're going to be looking at 365, okay? All right. Let's assume for all problems that we do that it's not leap year, so we can just go with 365. I guess really we should do 365.25 if we wanted to account for leap year. All right. Still got the 0.06 in the numerator, but the denominator there is 12. And I've got 12 times 9 in the exponent there. Okay, running out of space here. Okay, so I'm going to do this on my calculator. I'm going to start with that and kind of work my way out from there. Okay, so let's go ahead and do that. I've got 0.06 divided by 12. Okay, I'm going to add that to 1. So 1.005 is going to be my base. Okay, and then I'm going to raise that to 12 times 9. And 12 times 9, let's see, that's 90 and 18, right? 108. So I'm going to raise 1.005 to the 108. Okay, and then the last step is to multiply this all by 100,000. I'm not writing down all these steps just because I'm running out of paper here. All right, and I should get more money than the last time because this is more often, and you might think we're going to make huge jumps because we're going from twice a year to 12 times a year, but it's actually a little disappointing. It's not really that much more money than the previous time because it's going to slow down a bit. You make huge jumps as you compound more at the beginning, and then it gets, well, not huge jumps, but relatively, and then it kind of slows down a little bit. Okay, and then 365. Let's try this out. So this, we should be the richest of all with this one. I'm still leaving it in there for 9 years. So again, I'm going to start in here in my calculator. So let's see, 0.06 divided by 365. I'm going to add that to 1. And hey, this is in scientific notation, right? That means times 10 to the negative 4th. So this decimal has moved 4 spots left, 0.000164, blah, blah, blah. But anyways, okay, I'm adding this to 1. There's the contents of my parentheses. That's my base. I'm going to raise this to the whatever 365 times 9 is, which I'm not going to risk trying to do that in my head. Okay, so I'm raising it to that, whatever that is. Got this number, and my final step is to multiply by 100,000. And here's my new total. .07. Okay, and yeah, it's another 200 and some odd dollars than when we're compounding monthly. Okay, so that's it for today, and I'll see you next time.